and I try to stick to the time. So let's start really. Oops. This one, okay. As we are here at Seneca, quantum computing is out of an IBM perspective an approach where we like to leverage that in different types of technology. So we are talking about bits, neurons, and qubits, and Enrico was already talking about that, neuromorphic computing is part of that, quantum computing is part of that, and then we have the classical computing, so the classical supercomputing like here within Seneca. And looking to the right side, neurons and qubits, it's something totally different. So you are not programming those environments like in a classical way. It's a different approach, and you really have to learn to program that with, let's say, if you're good in linear algebra, then you're very close to really to program these environments. And I'm talking to my computer science students always, if you like to be in that world, you have to move out of your comfort zone with classical programming languages, and move in a different type of world to get access to those systems. But as already mentioned, those components are accelerators, extensions to the classical computing environment, which are controlled by the classical computing environment. And a good example for that is the Oak Ridge system. And we are still proud, it's still #1 in the world. So it was not beaten on the last supercomputing conference in Denver by China or by the Japanese guys. The systems were built, but so far as I'm knowing that, they were not capable to deliver the LINPACK performance benchmark to those systems. So we are still #1 and #2 in the world. The Oak Ridge system is a good example for this hybrid approach for the new world. We do have here also the Synapse chip, that's a neuromorphic chip from IBM, which is in place since a couple of years, and it's working mainly in the AI environment, and you're programming those chips totally different. The nice part here is we are talking about very low energy consumption. So one chip is just consuming 70 milliwatts. And compare that to a GPU from NVIDIA, you're burning really a lot of energy here in those environments. And with those technology, really you can reduce the footprint of the infrastructure, but you can also really scale out with your compute environment from the performance side. The pity here is no LINPACK is running on that, so it's not counting within the LINPACK environment. And the third component, what we incorporate here is quantum computing. So we incorporated the IBM Q system, and we also did run the simulator on the classical computing environment, where we were able to simulate a quantum computer roughly with 50 to 53 qubits. And just to give you a hint what the power of quantum computing means, if you like to double, if you like to add one qubit just to that simulation environment, you have to double the whole infrastructure. So it's really pretty close. We are talking about 53 qubits. That's the biggest system of IBM which we are actually providing. The potential use cases we are actually discussing with the IBM Q network and the members there from the IBM side are different areas to figure out really one of the first application which is really scaling out in classical computing environment. And there are some interesting approaches where we are looking at, and hopefully in the next 1 to 3 years we find something which is really of value. If a problem is not fitting within the compute environment of a quantum computer, you can also do it in an iterative approach with classical computing and quantum computing, which we are doing with many of our corporations we are having actually in place. For example, with the Oak Ridge system, but also with other environments. So where we are and where we like to go. So in 2016 we announced the IBM Q system. for the public environment. It's free, it's open source, and everybody really can use it. And the target is now to build some codes, some environments which really can benefit from quantum technology. And if we do have that, that's the time where quantum computing might be commercialized. That means you can make money out of that. And the approach will be the cloud environment, as we are supporting actually the quantum technology from the IBM side. There's a lot of discussions around the capabilities, quantum supremacy. IBM defined a term, it's called quantum volume, which is defining the power of a quantum computer. And it says it's consisting out of different components. So it's, in the first step, you really have to bring down the error rates, and then you can increase the amount of qubits. Otherwise, it's not giving you any benefit, just adding some additional qubits. And quantum volume is about the amount of qubits you are having, the error rate you are having with those qubits, how many qubits you can entangle each other, and what's the coherence time, so the lifetime of the overall system. Those 4 parameters really defining the capabilities of a quantum system. And you can have a bigger quantum volume with 5 qubits or 8 or 9 qubits than having one system where one of those parameters are really bad, but having hundreds or 1,000 qubits, but not giving you any benefit back. And that's the reason why we are always looking how to increase the quantum volume of our systems in such direction. And that's related also to the 53 qubits. Like the Moore's law, doubling every time, every 18 months, the capacity of the processors by transistors. We define something similar to the quantum environment. And one commitment we were giving, we are doubling every year the quantum volume of our systems, and we proved that. So even staying with 20 qubit, with the 20 qubit processor, we already have the 3rd generation in place. Every year we double the quantum volume for those systems. And the newest one is the 53 qubit system, which is available for the IBM Q network. So the community within the IBM Q network is having access to that system and really can run and work with that environment. And that's somehow different to many other environments. We are really providing with our technology to the community. And the 53 qubit system is really the last one we developed. It's the experience we made out of the 20 qubit systems, and we are now satisfied that we really can build bigger systems in such type of environment. And topology is really important, and that's the 2nd version of a 53 qubit system we built, because that's having a better error rate and better coupling connectivity than the 1st version, and you just change the architecture and getting something better out of that environment. And we are offering that also to the market with the IBM Q System 1, where clients, so industry clients, but also academic institutions, really can have their own system if they like. It was an announcement early in 2019, and quite just to remark that to Italy, that design was done by an Italian designer. So that picture and that layout is out of Italy. Let's fix that. So the IBM Q network was built out of requests from the academia and industry environment because of having access to bigger systems, but also everything what's IP related, it's difficult if you are doing that in an open source environment. When we are talking about quantum application, it's always related to IP. that guy who is really building the first application, which is giving you an benefit with that, will do some money out of that. And that's the reason why academic institutions, but also industry clients are asking, okay, let's have a separate environment, and with that, we build the IBM Q network. And I was also asked to talk a little bit about the Fraunhofer stuff, what we are doing. That's a quite different, let's say, membership within the IBM Q network, because the German government were asking IBM, can we have an on-premise system in Germany? And so far, all the systems are in the US. In north from Yorktown, we are actually building up a specific compute center where all the IBM Q system ones and systems are placed. We are actually, so we did a memorandum of understanding in September to move one system on an IBM environment within Germany, which is available for the German academic, but also the industry environment, and also we are talking about the European community. This is really something pretty new, and we will have that type of environment with a competence center, with a joint competence center with Fraunhofer together, up and running next year. So that's the plan, and we are actually negotiating the details. And hopefully, so in January, we will have a bigger press announcement with all the details behind that. And that's a big step for Europe and for Germany, I would say, really in that direction. The current IBM Q network is looking like that, 91 members, and the yellow ones are the European ones. So partners, hubs, members, startups, academic institutions. And we are looking everywhere in the world for those partnerships to work closely together with them to bring forward the technology. It's a research cooperation what we are doing here. It's not classical sales or something like that. So we are cooperating with our research, quantum research center, together with those guys to bring the technology and solutions forward. That's the distribution, more or less. As you can see, we are not running any business in China and Russia and North Korea out of these certain reasons. Okay, so what I always recommend to everybody who like to get deeper into the IBM Q story, join the IBM Q experience. It's free. Beginners tutorials to deep dives is available here for everybody. And learn about Qiskit. And Qiskit is not only running on our systems, it's meanwhile, because it's open source, used from different other vendors. And if you like to have the bigger systems, but also research cooperations with IBM on that, join the IBM Q network. Yeah. Quantum starts here. Quantum starts here at Seneca, and it's really a pleasure to be here with so many people and gathered so many people, and not do it like that guy here, eat up your chocolate from your kids, and wish you a Merry Christmas and a good session here. Thank you very much.
Thank you, Ingolf, for the nice presentation and being on time perfectly. So I'm asking you if there are some questions for Ingolf from the other room. I probably have one. Okay. So maybe a technical, but how you define on the side about the topology of the quantum qubit? So why you are not able to, let's say, have the full connectivity, and you have to decide a specific topology for the, in example, for the IBM Q? What drives the decision?
Okay, so you're building up these chips like a classical processor, so you're bound to the production environment like classical processors. And then you're placing your different qubits, and based on that, there are certain connections allowed or possible and certain not. So you're starting with the first approach, and then you are doing measurements, how the whole chip is behaving. And based on that, then you're doing changes to get out, let's say, more connectivity, so more qubits are connected to each other, but also related to the error rates. And the error rate is the biggest thing with the transmon qubits here. And based on that, you're making then your decisions, and it's somehow also a little bit try and error, to be quite honest, where to place the qubits and how to connect those qubits.
Let me try to understand. So now the decision is driven more by the error rather than the application.
Yeah. Absolutely.
That there was
no.
an application.
No.
Okay.
And you're building first the chip, and that's really the difficult part, to find an application which is really using that topology. And there are not so many people in the world who really can map a problem to these type of topologies. So we are looking for people who can do that.
Okay. Thanks.
Thank you.
Thanks a lot.